Now settle the curtailments here. Settle the reinforcement at the support. You will need to consider also the reinforcement from the adjacent beam. Do the calculations for the midspan of the adjacent beam, get the amount of reinforcement, and then see is the size of the reinforcement similar to the one here. This is of course after the curtailment. If the bar size are different, let's say here require 2H16 and here require 2H20, you're going to expect there will be lapping between the reinforcement. Again, you will need to calculate the lapping length. Try not to be confused with the statement here. The lapping for the two bar starts here and ends here. However, normally when we show the detailing, we refer to the grid line, indicating where the lapping length should end. Of course, you may also indicate the lappings where it starts and ends, depending on your preference, which in this case, everything refers to the grid line. We make it consistent throughout. Indicates that the amount of reinforcement bar here is 2H20. Probably you do not require any lapping length. You can have the reinforcement continuous. Only at the midspan here, you provide an additional reinforcement. However, you will need to be careful, especially when you deal with the continuous beam. Let's say this beam. This is the same beam that we are referring to, except that it is generated by the software as tip. For manual calculations, it is already quite tedious when you produce one section of the beam. But remember that when you produce the detailing, you are producing the detailings for the entire beam. Let's say for the continuous beam here, your first span is 5,600. Second span, it will be 6,000. And then the third one, it will be 5.6 meters. Assuming that you need 2H20 throughout. This is not achievable in the industry when no lapping is provided. The raw material, which is the steel bar, come with the maximum length of 12 meters. The total length now is more than 12 meters. That means somewhere along the beam there will be lapping length required. If you choose to have the 2H12 to be continuous, make sure the total length of that continuous rebar is not more than 12 meters. Before reaching the limits of 12 meters, you will need to provide lapping length so that stress can be effectively transferred from a reinforcement to another reinforcement. Now the next question is where you should put the lapping for the reinforcement. Normally for the bottom reinforcement bar, we will have lapping at the support. It is not recommended to have the lapping of the reinforcement at the high moment region because we have concern with the workmanship. That means the quality of the work. Having the lapping near to the support is beneficial, especially for the shear resistance. Because of the lapping, you have extra rebar to take the shear load. And you know that the shear loads, it will be higher near to the support. So this is about lapping with the reinforcement bar from the adjacent beam. Now that we have done with the main reinforcement at the midspan and the support, We also discuss about the curtailment, anchorage and lapping. Next, we deal with the shear length. In our previous calculations, the shear length required is R8, spacing 125 mm. These are for the normal shear length. As for the minimum shear length, you may provide R8 275, also calculated previously. Now, if you refer to the shear force diagram, you will see higher shear loads at the support, smaller shear loads at the midspan. That means you're going to expect providing R8 125, which is higher shear resistance at the support, and you're going to expect providing the minimum shear length, which is R8 275 at the midspan. As a start, you can sketch in this manner: normal shear length at both ends and minimum shear length at the center. Now the next step here, it will be for you to define where the normal shear length should end and where the minimum shear length should start. This will have to go back to your previous calculations. Based on the calculations, you know that the shear loads can be taken by the minimum shear length is 68.1 kN. Now refers to the shear force diagram. 108 kN at one end, 147.6 kN at the others. Draw two lines for 68.1. Knowing where the shear force diagram intersect at the 0 kN, then you can do some interpolations to find this distance. This 68.1 kN will set the boundaries of your minimum shear length. When this line intersect with the shear force diagram, this will be the regions of the minimum shear length, whereas these sections and these sections will be the regions for the normal shear length. You can do the interpolations by taking the ratio. The ratio of 108 versus the 2.367 shall be equals to the ratio of 68.1 versus this distance. Once you find this distance, use this minus the distance that you found, you get 0.874 meter. You will do the same for this, which end up to be 1.741 meter. And then coming back to your shear length now. This will have a distance of 0.874. As for this part, it will be 1.741 meter. The rest, it will be the minimum shear length. Once you know the locations where the respective shear length should end, now you will need to calculate the numbers of the shear lengths required. How do you do that? You use this length divided by the spacing of 125 plus 1 extra shear length. Why do you need to plus that extra shear length? Let's say you are dealing with this stretch of beam. The length here is 800 something. So you divide by the spacings of 125. That defines the number of spacing. So the number of shear length, it will be 1 extra shear length, so that it will give you the desired number of spacing. This is how we get that 8R8 125. Same principles goes to the others. Use 1.741 meter divided by 125. That gives you the numbers of spacing plus 1 extra shearing. That gives you a total of 15 shearing for this stretch. And then you will do the same for this. Once this is completed, next we deal with the cross sections. Indicate where you are doing the cross section, and then show the cross sections in accordance to the levels of the cross section. Let's say now the cross section here is AA. Then show your cross section here. Show the beam dimensions 200 and 450. Show the shearing, and then show the amount of reinforcement. For these cross sections, you have 2 H12. That means you will have 2 top bar and 3 H20. There should be 3 bottom bar here. You need to clearly indicate 3 bottom bars at the beam soffit. Let's say now if you are doing the cut section here, you will expect 3 H20, 3 bar at the top and 2 bars at the bottom if you are doing the cut section here, disregarding the lapping of the reinforcement. The cross sections will indicate to the contractors how the reinforcement bar shall be arranged. Done the cross sections. Next, we will indicate the column. The beam is supported by the column. When you show the column, you have to cross-check with the structural key plank the locations of the column as referred to the grid line. You need to know that whether the grid line is at the center of the column or the grid line is at the edge of the column. Now, if the grid line is at the edge of the column, it is at which edge? Is it column arranged in this manner or arranged in this manner? To know this, you will have to refer to the structural key plank. From the structural key plank here, the grid line, it will be to the center of the column. Therefore, now your column, it will be towards the center. The width of the columns, it will be in accordance to the size of the column. You may refer to the key plank or the specifications given. Not only that, you will need to check yourself whether the column stop at this level or is actually going up further. For a typical key plank, if the column is not going up, it is normally not H. Let's say now this column is H and this column is not H. That means you have this column going up, but this column stop at this level. In this case, if you sketch the detailing, this column is not going up, therefore it stops here, and this column will go up. That means you have to sketch to indicate the columns is going up here. Now that we have covered nearly all the essential items in the detailing of a beam, it may seem simple, but there are a lot of information needs to be incorporated in the detailing. There are many minor things that you have to pay attention. Some require proper calculations. That means in producing a detailing for a beam, it is not as easily as it is said. There are a lot of work behind it. Having gone through these videos, you have a better understanding in producing a standard detailing of a beam.